Hello, in this lesson we cover section 1.2, number puzzles and sequences. We will look at sequences and we will see two different ways to represent sequences. We can have recursive formulas and we can have closed formulas. We'll talk about converting between those two different forms and then we'll end with just a little bit on sums and sigma notation. Alright, sequences. So consider this sequence 4, 6, 8, 10, 12, and on and on and on forever and ever. We can give variable names to the terms of this sequence. So this 4 is like a sub 1, 6 is a sub 2, a sub 3, a sub 4, a sub 5, and so on. So I can say that the fifth term of the sequence is 12, the third term of the sequence is 8, and so on. So a recursive formula is a formula for the terms of the sequence in terms of the previous terms. Like, you can see that every term is 2 more than the one before it. And I can represent that by saying a sub n equals a sub n minus 1 plus 2. The general nth term of this sequence is, it kind of looks like the previous term, a sub n minus 1, then just plus 2. The one thing that this doesn't handle is, what about the very beginning? What about that 4? That 4 doesn't come from anything else. So we do have to specify the initial condition. We say initially a sub 1 equals 4. And then, once I have these two pieces of information, that a sub 1 equals 4, and that a sub n equals a sub n minus 1 plus 2, that gives me the recursive formula for the sequence. One last little bit of information, sometimes you see it, sometimes you don't. In this second part, a sub n equals a sub n minus 1 plus 2, sometimes you'll see a restriction like n greater than or equal to 2, because this second part only works if my subscript is 1 or more. All the subscripts here are either 1 or greater. Okay, let's move on to a closed formula. So a closed formula says I should be able to figure out just the term of the sequence directly. Well, 4 is, how do I get from 1 to 4? How do I get from 2 to 6, from 3 to 8, from 4 to 10, from 5 to 12? What do I have to do to 5 to make the 12? Is there some kind of pattern that says I do something to the 5 to turn it into a 12, and that pattern works also for the 4? I do the same thing to the 4 to turn it into a 10. Maybe if I double it and add 2, so I want to double the index and add 2. Right? Double the 4, add 2, gives me 10. Double the 3, add 2, gives me 8. So in general, I can figure out the nth term, a sub n, comes from doubling the index, 2n, plus 2. And that's our closed formula for the sequence. So the closed means that given any particular n, I can figure out the value of that term right away. So both of these ways of expressing a sequence are good. It's not like one is better than the other. And here are two examples, the 2 and 3, that show us why we might want one formula or the other. So let's say that you know a certain term of a sequence is of this sequence, so it goes out 4, 6, 8, forever and ever. You know that a certain term is 898. What would the next 3 terms be? Well, I don't have to calculate them all individually. I can just go on, keep adding 2. Just do this using the recursive formula. So, of course, add 2 to that, I get 900. Add 2 to that, 902. Add 2 to that, not 2, 904. And so on. So recursively I can figure out easily the next few terms. What about the 1000th term of this sequence? Well, I could just recursively go out, add 2, add 2, add 2, add 2, and do that 1,000 times. Or I can use the closed formula. A sub 1,000 is, okay, use my closed formula, 2 times 1,000 plus 2 equals 2002. Alright, so let's pause and take some time for you to try making closed and recursive formulas for a few sequences. Pause the video, and when you're ready to see the answers, start it up again. Alright, let's take a look at some of these answers. First one, let's see, the closed formula let me write the terms above: A1, A2, A3, A4, A5. So what do I have to do to the index in order to get the term? And this one grows, this sequence grows. It doesn't grow linearly. I'm not just adding the same number every time. The space between them grows faster and faster. So I add 3, and then 5, and then 7, and then 9. When you see spaces growing faster and faster, that's a clue that there might be a square in there. And in fact, if I square the 5 and add 1, I get 26. If I square the 4 and add 1, I get 17. If I square the 3 and add 1, I get 10. And in general, this formula is a sub n looks like n squared plus 1. For the next sequence, let's see, a1, a2, a sub 3, a sub 4, a sub 5. But these are powers of 3. This is 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4. So our closed formula, let's see, how do I get, it looks like a sub n equals 3 raised to the n minus 1. And for the recursive formula, actually the recursive formula is a little bit easier, right? I start a sub 1 equals 1, and then all I do is multiply the previous term by 3. So a sub n looks like a sub n minus, looks like 3 times a sub n minus 1. All right, for my next sequence, all I'm asking for is the recursive sequence. What do I do? Let's see, from 3 to 7, 7 to 11. Looks like I'm just adding 4 each time. So I start with 3, a sub 1 equals 3, and then a sub n equals the previous, a sub n minus 1, plus 4. And if we want to, we can say n greater than or equal to 2 for that. All right, this last sequence, everything is doubling. So actually, once again, the recursive might be easier. A sub 1 equals 5. A sub n is twice the previous, 2 times a sub n minus 1. But what about the explicit formula? So what if I pull out factors of 5? So 5, 5 times 2, 5 times 4, but you know what, let me call that 2 squared. 5 times 2 cubed, 5 times 2 to the 4th, that's a1, a2, a3, a4, a5. So it looks like the power of 2 is 1 less than the index. So a sub n is 5 times 2 to the n minus 1. All right, moving on. What about converting between the two forms? If I start with a sequence given recursively, how do I get the sequence in closed form? A good way to do it is just start writing out the first few terms. Write out the first few terms, maybe you'll see a pattern, and then you can write it out in a closed form. So let's do that. I'm going to list my n up here and the a sub n down below, and I'll give myself a little space. 1, 2, 3, 4, 5. So a sub 1, oh, that's given to us, that's just 1. How do I figure out a sub 2? Well, a sub n is the previous term plus twice the index plus 1. So it's the previous term, that's 1, plus twice the index, in this case my index is 2, twice the index plus 1. So that looks like 6. All right, how about a sub 3? A sub 3 is the previous term, there's the 6, plus twice the index, that's twice 3, plus 1. So 6 plus 6 plus 1 is 13. All right, a sub 4, I start off with the previous term, plus twice the index, plus 1. 13 plus 8 is 21, plus 1 is 22. All right, and one more time, the previous term, plus twice the index, plus 1. That looks like 22 plus 11, which is 33. Now that I have my first 5 terms, let's see if we can figure out what is the closed formula. How do I get from 1 to 1, from 2 to 6, from 3 to 13, 4 to 22, 5 to 33? What's the process that lets me go from the n value to the a sub n? If you want to pause and try for a minute or two, I challenge you to do that. It's a little bit tricky, but maybe you can do it. Otherwise, I'll go ahead and ruin the surprise. There are a couple ways you can look at this. First of all, it's not linear growth. The space between these terms is getting bigger and bigger, so something with a square in it is a good guess. 3 squared is 9. That is kind of close to 6. I'm sorry, 2 squared is 4. It's a little bit under. 3 squared is 9. 4 squared is 16. 5 squared is 25. I don't really see, it doesn't exactly work. Like 2 squared, I'd have to add, is 4, I'd have to add 2. 3 squared is 9, I'd have to add 4. The trick is actually, if you notice, going backwards. Like 3 squared is 9. And how does that compare with 6? 9 is 3 more than 6. 4 squared is 16. That's 3 more than 13. 5 squared is 25. And that's 3 more than the 22. So that's where our solid pattern starts to emerge. So a sub n is, so like this 6, is, I'm going to square the one index number higher. So n plus 1 squared, and then I subtract 3. And there is a closed formula for the first 5 terms. Now, sometimes you might have noticed a different pattern. Some people notice this. What if I take the 1 times the 3? 1 times 3 is 3. How about that? 1 times 3 is 3, and that's 2 more than the 1 down below. 2 times 4 is 8, and that's 2 more than the 6. 3 times 5 is 15, and that's 2 more than the 13. So you might see the pattern a sub n is n times n plus 2 minus 2. And at this point, I will leave it to you to maybe algebraically work these two sides out and convince yourself that they really do equal the same thing. All right. Let's go in the other direction. Let's say that we start with a closed formula. So in this case, the value of the term of the sequence is given to us explicitly in terms of n. Let's see, the first 3 terms. A sub 1 is 1 squared plus 10, which is 11. A sub 2 is 2 squared plus 10, which is 14. A sub 3 is 3 squared plus 10, which is 19. Okay, we have the first 3 terms. That was easy enough. That was easy to do with this explicit formula. Now let's prove that this is my recurrence relation. This gives us the recursive form of the sequence. So if this is the initial value, I do have my initial value up here. So initial value. And then this part is called the recurrence relation. So let's prove that this is the proper recurrence relation for that closed formula. And I'll go to a new slide and start right on top. Okay, the trick is, start with the really big complicated side and simplify that down to see that it actually equals a sub n. All right, so here we go. A sub n minus 1 plus 2n minus 1 equals. Now what am I going to substitute for a sub n minus 1? I know my closed formula. A sub n is n squared plus 10. Well, a sub anything is that thing squared plus 10. So a sub n minus 1 is n minus 1 squared plus 10. That's the a sub n minus 1. And then I need to add plus 2n minus 1 there. And now I have the right-hand side, which is totally in terms of n's. It doesn't have any a sub n's in it. And it will just expand everything out. So it looks like we get n squared minus 2n plus 1 using FOIL plus 10 plus 2n minus 1. Do some simplification. The n squared stays. it looks like I have a minus 2n and a plus 2n, so those drop away. And then my constants look like 1 plus 10 minus 1 just leaves me plus 10. But look at this. This n squared plus 10 is really just a sub n. So I've done it. I've shown that a sub n minus 1 plus 2n minus 1 equals a sub n. That was exactly what I wanted to prove. All right, here's one for you to try. Prove that the sequence a sub n equals n squared plus n satisfies this recurrence relation. So pause the video, give this thing a try, and see if you can prove that this recurrence relation works. All right. Did you do it? Did you really try? I'm trusting you did. Let's see how it actually works. So I'll start with the big complicated side. A sub n minus 1 plus 2n. And this becomes n minus 1 squared plus n minus 1. That's my a sub n minus 1. And then I still need to add 2n to that. Expand n squared minus 2n plus 1 plus n minus 1 plus 2n. What falls away? My n squared remains. I have a minus 2n plus 2n and a plus n, so plus n stays there. Plus 1 and the minus 1 fall away. Oh, so that's all I'm left with. N squared plus n, and I look above. That's exactly what I was looking for. So that really is a sub n as needed. Here's a famous sequence. It's nice to include this one in any kind of discussion about recurrence relations and recursively defined sequences. The famous Fibonacci sequence. So if you've seen this before, then you kind of know how it goes. But if you haven't seen it before, take a look here and see if you can figure out how this recurrence relation works. Now, the Fibonacci sequence is a pretty famous sequence, so we don't just use a sub 1, a sub 2, a sub 3. We actually denote the terms of the sequence with a capital F. So capital F sub 1 is 5. It is 1. Say 1, 2, 3, 4, 5, 6, and for example, F sub 6 equals 8. The sixth term of the sequence is 8. Well, the recursive formula for this sequence is that F1 is 1 and F2 is 1, and then the recursion builds off of both of those. F sub n looks like F sub n minus 1 plus F sub n minus 2. And so you can see how 2 plus 3 equals 5. 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. So every term is the sum of the previous two. So F sub n is the sum of F sub n minus 1 and F sub n minus 2. Well, could we use some of the tricks from the previous slides now that we have a recursive formula? Is there some way that we could figure out a closed formula, or in other words, an explicit? Sometimes you see explicit, sometimes you see the word closed. It means the same thing. I sometimes challenge my students to think for a few minutes and try to come up with a closed formula, and inevitably they fail, sadly, because it is not obvious what the explicit formula is. All right, well, here is the explicit formula. Well, I'm sorry, there's the recursion, and here is the explicit formula for the nth Fibonacci number. Not obvious. It is not intuitive how you would get that. All right, moving on. Sums and sigma notation. So write 2 plus 4 plus 6 plus 8 plus 10 plus 12 using sigma notation. So sigma notation means that we find a nice compact way of expressing sums like this. So what is the pattern here? This is really like 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6. So all of these terms have the form 2k, where k goes from 1 to 6. So I put a big capital sigma in front of that, and I write k equals 1 on the bottom and 6 on top. And the sigma is kind of our way of saying add these things together. Sigma is like S for summation, so sometimes this is also called summation notation. So this is really 2 times 1 plus 2 times 2 plus on and on until I get 2 times 6. What about going the other way around? Here is a sum that's given to us in sigma notation. How do I turn it into an actual number? Well, I can start by starting with k equals 0. It doesn't really matter what the k value starts with. It often starts with 0 or 1. So this is the same thing as 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. I'll make that 4 look a little bit better. And so that looks like 1 plus 2 plus 4 plus 8 plus 16 plus 32. And that ends up being 63. All right, I'm not spending a lot of time on sums and sigma notation, but it's not too hard. It's pretty straightforward, and use some of the problems to help you get more comfortable with that if you need it. And that's where this lesson ends.